This is October, November 2023, paper 42. So first he says define the radian. So we understand that radian, it's just a basic definition that it is actually an angle subtended at the center of a circle when the arc length is equal to the radius. So if this is a complete circle, the radius and the arc length are both, if they are both equal, the angle at the center is said to be as 1 radian. Okay? And generally it is always 57.3 degrees. So in the next question he says that the minute hand of the clock revolves at a constant angular velocity or angular speed, 1 revolution every hour, and there is a mass attached to the second hand with a distance L. Okay, fine. So calculate the angular speed omega of the minute hand. So we can do that very easily. So this would be omega is equal to the angle divided by time taken for that angle to be covered. That is a complete 2 pi angle, which is 360, divided by the minute hand, which is, sorry, this is, yes, a minute hand. So this will be taking 1 hour. So 1 hour multiplied by 60 minutes multiplied by 60 seconds. This will give you 1.7 into 10 raised to power minus 3 radians per second. So write this answer over here. Then we have during a time interval of 1400 seconds, the center of gravity of the mass modeling clay figure 1.1 moves through a distance of 0.144. He says calculate the angle through which the minute hand moves in this time interval. So we still have the formula as omega equals to 2 pi divided by t, but since this is the full circle, full angle, the actual formula is theta divided by time taken, or the angle divided by time taken. So the angular velocity is 1.7 into 10 raised to power minus 3. So let's write that down over here. So this will be 1.7 into 10 raised to power minus 3. Theta divided by time is 1400 seconds. So this is 1400. So theta comes out as 2.38, which will be 2.4 radians. Similarly, determine the distance of, or determine the distance L, which requires you to employ the formula for circular motion, right? So the whole formula goes something like this. If this is the circle, and let me draw this again. So if this is the circle, right? And whatever the radius may be, for example, if this is the radius, and this is the arc length, the distance that he's mentioning over here that he's covered, 0.44, is actually the arc length. So it moves through this distance. So this is 0.44 meters. The angle at the center we know is 2.4, right? And we want to find the length L, which is the radius effectively. This is the length L. So what are the formulas that connect them together? So the formulas go something like this. So theta is equal to arc length divided by the radius, right? So we have the theta. Theta is 2.4 radians. We have the arc length, which is 0.44, but we don't have the radius. So replacing both in these equations, radius comes out as 0.183 meters. So this is 0.18 meters. Calculate the magnitude of centripetal acceleration. Very simple. So this will be A equals to R omega square. So what's the radius? That is 0.18 into omega, which is 1.7 into 10 raised to power minus 3 whole square. So the acceleration comes out as 5.2 into 10 raised to power minus 7 meters per second square. A very small value, but it is expected because the minute hand moves very slowly. Use expression in C3. What have we done in C3? Okay, so use your answer in C3, which is this one. Explain why the variation of the time, the magnitude of the force exerted by the minute hand on the piece of the molten clay is negligible as compared to the minute hand, or as the minute hand goes through the full rotation. Basically what he's trying to implore is that, for example, if there was an object or the merry-go-round play toy that students, or you can say the children, actually experience, what happens in that situation is that it's moving so quickly that in certain situations the force exerted feels greater than its own weight, right? I've explained this phenomenon, explained this in another video of circular motion of A levels. I will attach the link in the description. If you want to explore more about this, you can go and check that out, check that lesson out. So in short, what happens is that if it is moving ever so slowly, then this acceleration will have no effect on this, and you can check this by F equals to ma. The force due to the centripetal acceleration will be so low in comparison to the weight of the object that its effect will be negligible. So whatever I'm discussing right now, we have to write this down in a statement form. So we will say that the centripetal force or the centripetal acceleration is much less than the gravitational acceleration, or the value of g, which is 9.8 meters per second squared. You see, when you compare values, and if you know as a fact that another value is already known and is compared with something that is calculated before, then it is a good idea to suggest why do you think that this is much less than this value, because you know that this value is much higher. So the examiner knows that you are talking about the gravitational acceleration. So we can comment the centripetal force is much less than the weight of the object, because of course we're eventually going towards ma being compared with mg. Okay. All right, moving to the next part, define gravitational potential. This is a very highly repetitive question or a definition. So we define this as the amount of work done in moving an object from infinite distance, or from infinity to that specific point. The second part is the moon may be considered to be an isolated uniform sphere. Okay, thank you, fine. Where it has a mass of this value and it has a radius of this value. Calculate the gravitational potential at the surface of the moon. Very simple. So the gravitational potential is negative gm over r. Now since this is the moon itself, what will this value represent? So we are imagining that an object is placed at infinity distance. Let's say this distance is infinite. And if we throw this object, if we let this object to fall down, it keeps falling down due to the gravitational attraction. And when it lands on the surface of the moon, how much energy will it have? Now, since we don't know the mass of this object, we talk about the gravitational potential, because that is joules per kg. Now, this is a good idea in terms of calculation, because if I know that how much energy is possessed per unit mass, then any mass being thrown or being brought from an infinite distance to that point can be just simply be multiplied with the gravitational potential, and we will find out the gravitational potential energy. So 6.67 into 10 raised to the power minus 11 gravitational constant multiplied by mass divided by the radius, which is 1.7 power 6. Now this, I say radius, but this is actually a distance. Again, in comparison from the center of the mass to this is infinity, and this distance is the surface of the moon itself. So how much energy will it possess? How much potential will it have? So when you calculate this, this comes out as negative 2.9 into 10 raised to the power 6 joules per kg. If you multiply any mass, let's say 5 kg of mass, that would mean that if a 5 kg mass of an object falls on the moon, simply previously we used to do this by mgh, but we can't do that again, because in A levels the value of g is changing at all times. In mgh we assumed it to be 9.8, but over here it's changing. So by any hypothetical mass, if we multiply, we will get to know how much gravitational potential energy it will have when it falls down. So this is gravitational potential. So that will be negative 2.9 into 10 raised to the power 6. Unit will be joules per kg. The next point is an isolated system sphere has a gravitational potential phi at the surface. Okay, fine. Particle of mass m again leads to the same idea. It says determine expression. This is what I've already discussed. If you want to find out the gravitational potential energy, which is represented as EP, that would simply be potential multiplied by any mass. And if you look at their units, it becomes self-explanatory, because the potential unit is joules per kg. If you multiply this with mass, then mass gets cancelled out eventually. Mass cancels mass, and you're left with joules only, which was the previous target to finding the gravitational potential energy, mgh. But we used to do this in O levels because the value of g stayed 9.81. In A levels, the formula has changed to minus gm over r multiplied by mass. Now this mass gets multiplied separately, because first we need to accommodate for the changing value of g, and that changing value of g actually translates into gm over r. So eventually this formula becomes m phi. Show that the speed v of the particle projected upwards from the surface of the planet is given by this. Okay, no problem. So the logic would be that the gravitational potential energy is being equal to the kinetic energy. right? You throw the object with kinetic energy, converts into gravitational potential. No problem at all. So this will be simply phi m equals to half mv square. Now m cancels out, 2 goes over there and under root goes over here. So this becomes v equals to, now of course there will be a negative sign over here because of the gravitational potential, right? Yeah. So this will be negative 2 phi. Now if you are if you take A-level mathematics or O-level mathematics, you will realize that a negative under root does not exist. It's an imaginary number. So do we need to worry about this? No, because phi is always calculated as a negative value. So when you put in phi over here as a negative value, that negative multiplied by this negative will lead to a positive answer. So no need to worry about this for the future. A particle is moving upwards at the surface of the moon. Show your answer or use your answer in A2. So what have we done in A2? So in A2 we have found that the value of potential is negative 2.9 into 10 raised to power 6 joules per kg. And in B2, it's always a good idea to write down what he is mentioning, what he is referring to. And in the B2 part, we had a formula of V equals to negative 2 phi. So this is the information that he wants us to use to find answers for this part. Then he says, find the minimum speed of this particle that would result in escaping. So it's an escape velocity question. So again, the reason behind this already calculates, already mentioned, we just have to put in the value. So V equals to, I'm not writing down the negative number because negative and negative get cancelled out. So this will be 2.9 into 10 raised to power 6. We calculate the velocity, it will be 2408 meters per second. This will be 2400. Part D says that the hydrogen may be assumed to be an ideal gas. Okay, the mass of the hydrogen is this much. Calculate the RMS speed at 400 Kelvin. So this is a topic from ideal gases and we have a formula for this. And that formula originates from the idea that the kinetic energy of any gas molecule will be proportional to the temperature of the system. And if you go back to your books and refer to the syllabus, this equation comes out as half m RMS square equals to 3 by 2 kT. This was one of the proofs that we do in ideal gases, right? Okay, so mass of the gas is given, so let's plug in the value. So 1 over 2 into mass is 3.34 into 10 raised to power minus 27. C square as the RMS speed equals to 3 by 2. Boltzmann constant is 1.38 into 10 raised to power minus 23. And T is 400 Kelvin, already given to us. So when you take the under root over there, and of course by taking all the values first on the right side, we get C to be equal to 222.6 meters per second, which will be 2200 meter per second up to two significant figures. The previous velocity we calculated was 2400. So this is the escape velocity, that an object must have this much amount of velocity to escape the environment of the moon. The hydrogen gas that we found is moving at a speed or an average speed of 2200. That is why this is called an RMS speed, because this is an average speed. This is not a representative of every single particle that may be moving faster than this or may be moving less than this. It is just an average value. He says the surface of the moon reaches temperatures of approximately 400 Kelvin, okay, under direct sunlight. He says using an answer in C and D suggest a reason why the moon does not have an atmosphere containing hydrogen. You see, a hydrogen atom should have had 2400, but our hydrogen atoms are only heating up or only getting up to a speed of 2200. This is where the RMS concept comes in. This is where the average value comes in, that this is just an average representation, right? So many molecules may have greater than 2400 and eventually escape. Now we give a reason why 2200. What is 2200? 2200 is an average value, is an average RMS speed. Other particles may have different speeds than this, right? Okay, question number 3. What is meant by the internal energy system? Again, a repeated question, repeated definition. I would advise you to go through at least 4 to 5 years of papers and just memorize all these definitions or make notes of them. It is simply sum of randomly ordered kinetic energy and potential energy of all gas molecules. right? Use the first law of thermodynamics, which is delta U equals to delta Q plus delta W. Q is heating, W is work done. Work done could be due to a change in shape, due to a change in pressure, due to a change in volume of the gas, and or any sort of work done depending on the system. Q will be primarily heating only, heating or cooling. So of a spring, comment about what happens to the internal energy of a spring. Now, very odd question. When it is stretched at a constant, now if the temperature is constant, that means that the delta Q variable in this equation is going to be equal to 0, which means that the equation actually summarizes to this system, that delta U was equal to delta Q plus delta W. Now, since the heating is no longer a part of the equation, this whole system becomes 0. So delta U now entirely depends on delta W. Now, W is representative of a work done. So have we done some work on the spring? I think so. We have done this by stretching it. So yes, by stretching the spring, we have done a work of half kx square, or if you remember, we've done a work of half fx, right? So the amount of work done we've done on the spring increases because we're stretching it, or compressing it would have done the same thing. That would now increase internal energy. So this is what we have to justify in terms of statements now, right? So you mentioned that there is no exchange of thermal energy. So because the temperature is constant, you will write down, since the temperature is constant, the delta W becomes equal to 0. You will write this down, everything in English, right? Delta W becomes equal to 0. And internal energy, which is delta U, is now entirely equal to the change in work done, or the work done provided. Since work is done in stretching the spring, delta W increases, hence delta U also increases, right? Okay. The second part is of a sample of water when it evaporates from a rain puddle on a hot day. So we have what happens to the internal energy. The basic question remains the same for part 2 as well. So let's try to figure this out. So there is a sample of hot water or a puddle of water on a hot day. So this is a key information. If the day is hot, for example, then the delta Q exists, which means that thermal energy is being transferred. So what does the equation look like now? Again, it's an accounting problem. So this is delta U equals to delta W plus, sorry, let's write this down properly. This will be delta Q plus delta W. Now, if there is a heat exchange, if there is a hot day, that means we are providing thermal energy to the system. Now, if thermal energy is being provided, then that can do two things at the same time, right? It can either do some work, it will either be utilized to do some work, or it will be utilized to increase or decrease the internal energy or the internal energy reservoir, right? So it says that it is evaporating, which means that the work done is being done as P delta V. The gas is expanding because when it converts into a water vapor, it has to push back against the atmospheric pressure and escape into the environment. Of course, this job does not happen easily. It requires energy. So that will exist in the form of delta W. That means that the amount of thermal energy that we've provided will be utilized as work done, right, for the expansion, plus some of it will also go into the internal energy. Why? Because on a hot day, no matter whatever you do, no matter whatever thermal energy you provide, all of it cannot be utilized, all of it will not be successful in converting all of that into evaporation or water vapor. So whatever extra is left will be converted into the internal energy. So it could look something like this, that we provided, let's say 1000 joules of heat energy from the environment, from the atmosphere. Approximately 200 joules is utilized to do expansion for the evaporation, right? And the remaining 800 will go into the internal energy or the internal energy reservoir, right? So let's write this down. We will start from the thermal energy. This is step number 1. This will be step number 2, and then we come to step number 3. So you will say that thermal energy is provided, thermal energy given, absorbed or provided, causes gas or causes liquid to expand, causes liquid to expand and become gas as evaporation needs energy. So gas molecule pushes back, or you can say does work, which one? P delta V. Against what? Against the atmospheric pressure, then full stop, and the remaining energy increases the delta U, which is the internal energy of the system. Okay, so there is a chronology, there is a step-by-step process. First we justify this, and then conclude on internal energy, because that is the ultimate goal that he's asking us. Okay, going to question number 4. This question has a troubling, you can say there is a trick to this at the end. Okay, so it's an electron. This is the key information that will help us solve that question or get past that trick. Okay, so let's see. So in a metal rod moves randomly about a mean position, the electrons, and this is one of the simple harmonic motion cases. So this is, let's say, a rod or a piece of wire, and this is an electron. If you pass AC electricity, the electron is practically oscillating between two fixed mean positions. That's why it's called an alternating current. So whatever situation he's mentioning over here is true. We understand that. When an alternating current is passed, okay, we have accepted that. There is a simple harmonic motion. Okay, figure 4.1 shows the variation of time. Okay, fine. So this is the displacement of an electron, right? Determine the amplitude of the oscillation. So we can see that there should be a mean position at the center. This will be our mean position. But how do we calculate the amplitude? So what we can do is calculate the total height and simply divide this by 2. So we will get the amplitude of one side. So if you count the boxes at this point, this will come out as 7.2, and this minus 15 comes as it is. So 7.2 into 10 raised to the power minus 15 divided by 2 goes to a value of 3.6 into 10 raised to the power minus 15 meters. Determine the angular frequency. The angular frequency goes something like this. So omega is equal to 2 pi by t. So a complete oscillation of 2 pi takes how much time? How much time does it take? So you can take this from the graph very easily. You can either measure from this point to this point, count the number of boxes, or you can go from this point to this point. Or you have another choice. You could have done, let's say, from this point to this point, or this point to this point. Basically one complete wave in any format, any shape or size that you're comfortable with. Now simply pick the values from the graph over here. Sorry, not over here, but time is already mentioned over here. So when you count the number of boxes, you will find that the time comes out as 0.2 probably. Yeah. So this is 0.2 into 10 raised to the power minus 6. Where this minus 6 comes from? Be careful. This is microseconds, right? Okay. So this omega comes out as 3.14 into 10 raised to the power 7 radians per second, which is a very high value. 7.14 into 10 raised to the power 7 radians per second. User answer in A1 and A2. What is the A2 answer? This is the A2 answer, and this is the A1 answer. To calculate the maximum drift velocity or drift speed of the electron. So to find out the velocity, we had the formula omega under root x naught square minus x square. And we understand that v approaches maximum velocity when x becomes equal to 0, when this factor becomes 0, which means that the object is actually turning back to its mean position, right? So the formula goes something like this. So omega under root of x naught square. Now under root cancels out, so this becomes omega x naught. So simply that is 3.6. So let's multiply omega first. So omega is 3.14 into 10 raised to the power 7. X naught is the previous one, which is 3.6 power minus 15. This comes out as 1.13 meters, 1.13 power 7 power minus 7 meters per second, which is a very slow speed, right? This is what we used to discuss in classes as well, that the drift velocity at an AC level or at a DC level is very low as compared to what they are moving at when there is no voltage applied. So the rod has a cross-sectional area of this much. This is the area A. Charge density N. He says that all of the electrons are conducting, assumed to be in phase. This information will prove critical for the graph in the next part. So using information in A3, which is this information, which we have already calculated, to calculate I naught for the maximum current in the rod. No problem. So the formula of I is equal to, that is NAQT. If you remember, NaQV. So this is NaQV. What is the charge density given in the question? That is 8.5 power 28. What is the cross-sectional area? That is 4.3 centimeter square. So it has to be converted into meter square. So this will be 4.3 divided by 100 square into this will be 1.6 into 10 raised to the minus 19. V is the velocity which was previously found as 1.1 power minus 7. So when you multiply all of these numbers together, you will get 0.643 amperes, which will be 0.64 amperes over here, right? Moving on, this is where the troubles begin. Now, seemingly the question is for 2 marks, but there is a big catch over here. Now, he says that you need to sketch the graph of current. Okay, seemingly looks very simple, but first we need to do the equation analysis, what current depends on. So current is equal to NaQV. This is a constant, this is a constant, this is a constant. So I is dependent on V. Let's go back. What was V dependent on? So V was dependent on omega and x naught. Okay, all right. So let's write down V in terms of that. So V was proportional to omega x naught. Which of the quantities are a constant in this? So omega is a constant, right? That is a 2 pi f or 2 pi by t. It remains fixed. So naturally, we are actually coming down to this equation V proportional to x naught. Now let's get rid of the V. So current is proportional to x naught. This is what we are looking for. Why? Because we have a graph of x naught in the question. This is the graph for displacement. We want to draw the graph of current. So they should be proportional to each other, right? But there's a problem. The problem is that in simple harmonic motion, we know that whatever the graph of displacement may be, the graph of velocity is actually a derivative of the displacement. So if I go back and realize what this equation is, this graph of displacement actually is a negative sine theta graph, right? This is a negative sine theta. So if I take the derivative of sine theta to find the graph of velocity as we do in simple harmonic motion, the negative gets carried as it is and this becomes cos theta. So technically, I should draw a graph of negative cos theta for the velocity, for the current, right? So these are my extremes. Let's point them out first. These are my extremes, and these are the time periods where the complete wave actually formulates. Now, the graph of a negative cos theta actually looks something like this. It should go towards, let's say this is our 0.2. This will be our peak. This will have a low point. This will be low point. This will be the central points, high points, and low points and low points. The graph of cos theta should look something like this. Like this. This should be our final answer. Now, on the face value, this looks right. It should have been the final answer. But there is a problem. The problem is that this graph is for the electrons. This is for the electrons. The graph or the question says that electrons are oscillating in phase with the same amplitude, right? So if this was my reference graph, if minus sine theta was my reference, the derivative becomes minus cos theta for velocity and then for current. It's fine, it's right. But the value of current that we calculate, or the value or the formula of I equals to Q by T that we treat or that we so much so entertain, is basically for the conventional current. It's for a conventional current graph, right? So what should I do now? This graph will be flipped. Why? Because there is going to be a negative sign on the outside representing that if this is for the electrons, if this graph shows the directions of electron, to find the direction of conventional current, we have to go opposite to the electrons. Now, when you get to the opposite of the electrons, you have to add a negative sign in terms of mathematics. Now it becomes an equation for conventional current. So in reality, this graph would actually go something like this in terms of the blue graph that we are drawing. This is the right answer. So we remove the red graph and we settle down for this graph. Now, even if you go to this length that the derivative should have done this for me, so let's do that over here. Let's do that for this graph to clear out the confusion even further. Why this is happening, right? So this is the displacement equation, right? And the velocity graph is actually the derivative of the displacement. So what's the gradient at this point? It's highly negative. So my value should be maximum negative of velocity. So what's happening at this point? The gradient is 0. So my velocity should become 0. Again, positive gradient, so maximum positive value, right? Again, 0 gradient, 0 value for velocity. So when you end up making this graph, it actually looks like a cos graph. This is the graph of cosine, right? This is what we should have gotten. But this is the graph for an electron. This isn't for an electron. For a positive charge, I will have to draw the opposite graph, which is going to look like this. That is why this graph is drawn like this. It's a positive cos theta. Okay? All right. A very seemingly small detail that we miss generally is because of the electron. The graph has to be inverted at the end. So next question, he says that find an expression in terms of I. I can agree with a few students on this one that it's a very poor way of asking the question, that this is what you're looking for. I naught cos of omega t. So do we have a value of I naught? Yes, the maximum current was 0.64 cos. Do we have a value of omega from the previous parts? Yes, the angular frequency is 3.14 power 7. So this will go as 3.1 into 10 raised to the power 7 t. Now this is an expression in terms of time. Now what's happening at this point? I will choose t. It will be of my choice, and it can span from this point to this point. This is what the t is for, right? And when you put that t over here, including the microsecond or millisecond, whatever prefix there is in the question, you will get those answers for current that are actually representative of this graph that we just sketched. Next, 2 root mean square, no problem. So we understand that the IRMS value is equal to I peak divided by under root 2. So 0.64 divided by under root 2 gives me 0.453, which will be 0.45 amperes. State Coulomb's law. Now Coulomb's law, the formula for Coulomb's law is this one, exactly like the gravitational law. F equals to Q1, Q2 divided by 4 pi epsilon naught R squared. So we simply write down that the force of attraction, or the electric force, we just define the formula. The electric force is proportional to the product of charges. Notice what we've done. Is this not the product of charges? Yes. And inversely proportional to the square of their separation. Some students go ahead and say the square of separation between their centers, right? Where do we see the square of separation? Is this R square not a square of separation of the charges? Is this not written in terms of English, right? This is that R between the charges, right? So this is just the formula explained in English. Two identical, when he says identical, it means Q1 is equal to Q2. Oil droplets are in vacuum. The center droplets are distance of this much. There is a force this much holding them together. Magnitude of the charge on the droplet. Using Coulomb's law, Q1, Q2 divided by 4 pi epsilon naught R squared. This will become Q squared divided by 4 pi. This is 8.85 into 10 raised to the power minus 12. R square is this 3.8 power minus 6, so this is 3.8 into 10 raised to the power minus 6 whole square equals to F, which was given as 6.3 into 10 raised to the power minus 17. So take everything over there. Don't forget to take the under root, because this is a Q square. Q squared because they are identical. Identical means they are equal. So Q multiplied by Q becomes Q squared. Take the under root at the end, and Q comes out as 3.18 something. Power minus 18, probably, no, minus 19. So this becomes 3.2 into 10 raised to the power minus 19 coulombs, right? Now this previously was called Millikan's oil drop experiment. This was actually a part of the experiment, so for the syllabus, but they removed the name of this. So he says there are two horizontal plates. Okay, fine. There is an oil drop at the center. Good enough. There will be its weight, and probably it's held together due to the electric force on the oil droplet between the metal plates. A potential difference of 1200 is applied. The top is late. The oil droplet is stationary and is in equilibrium. State the sign of the charge on the oil droplet. You see, if it has to stay attracted or stationary or subtended, then this is a positive plate. It should be a negative plate so that the electric force can be acting against the weight of the oil droplet. So this becomes that the charge is supposed to be negative. He says, draw the electric field lines. Very easy question, very straightforward. If this is a positive plate, the electric fields are from positive to negative. He says 4 lines have to be drawn, no problem at all. So we draw 4 lines. Please use a lead pencil and a ruler for this. And they should be pointing downwards, as the electric field is always pointing from positive to negative. You get the full marks for this. He said the distance between the plates is 5.2. Determine the mass. Now, we start with the logic that the electric force has to be equal to the weight of the oil droplet. So electric force is QE, electric field multiplied by charge, and weight is simply mg. Then for electric field, we have 2 formulas. Electric field is equal to force per unit charge and voltage divided by distance between the plates, and Q divided by 4 pi epsilon naught r squared for a point charge. For plates, this is what we get. Now, this is the formula that we rearranged to get QE. So what are we left with? We're left with V by T. So E should be V divided by D equals to mg. What are we supposed to find out? We're supposed to find out the mass. So let's take G over there. So this becomes M equals to QV divided by, D and G. Let's replace the value. So this is a 3.2 into 10 raised to the minus 19. Voltage given in the question was, I think, 1200 divided by the G, which is 9.81, and the D, which is 5.2 centimeters. So this will be 5.2 power minus 2. When you calculate all of this, this M comes out as 7.5 power minus 16. So we can simply write this down as 7.5 into 10 raised to the minus 16. Question number 6 is about capacitors. We can see that there is only one capacitor in the circuit. It has a voltage of 8 volts. So the capacitor is going to act as a battery. Over here, the switch is open, the switch is closed at time t equals to 0, which means that the graph actually starts when the switch is closed. Alright, so voltage and charge is given. He says, show that the energy is 1.8 millijoules. So the energy can be calculated as half CV square or half QV. So I can see that there is a Q and a V over here. So this will be actually energy represented as area under the graph. So we have to be clever about this. So just replace the values as 1 over 2 QV, 1 over 2 maximum charge taken from the graph at this point and at this point. Please make sure that you count the number of boxes, and this becomes 450 into 10 raised to the minus 6 into 8, which is the voltage. So this becomes 1.8 power minus 3 joules. So we have shown what the examiner asked us to show. The next part says that determine the capacitance of the capacitor C. Give a unit for your answer. That is usually farads. So let's first write down the unit of farads, right? So the capacitance can be found by this formula, which is half CV square, which is equal to the energy 1.8 power minus 3. And we want to find the capacitance. So let's take everything over there. So this becomes the voltage is taken from the graph, from the figure, which is 8 volts. We already know this. So this will be C is equal to 2 multiplied by 1.8 power minus 3 divided by 8 square. So when you calculate this, this comes out as 5.6 into 10 raised to the power minus 5. Next we have this graph. Looks scary, but don't worry. So he says that show that when t is equal to 1 time constant, the value of ln is equal to 1. So what is a time constant? So time constant tau is equal to RC. This actually tells you that the value of the voltage of the capacitor may reduce by 63% after 1 time constant. Okay, so that is basically a tell, or you can say it's basically a representative of how the values are going to reduce in terms of the time that is incoming. Now let's look at the equation of the decay for the capacitor. So this is V is equal to V naught e raised to power minus t divided by RC. Now RC is the time constant, which is tau. Now what is the V naught? Do we know that? Yes, we know. That is the standard voltage or the starting voltage or the initial voltage of the capacitor, which is given in the question. So let's replace that. So V is equal to 8 e raised to power minus t by RC. Let's take this over there. So this becomes V divided by 8 equals to e raised to power minus t by RC. Let's take natural log on both sides. So this becomes ln of V divided by 8 equals to negative t by RC. Okay. This negative goes to the other side and this becomes negative ln V divided by 8 equals to negative t by RC. Now it says that when t becomes equal to time constant, now this RC is a time constant, which is going to be equal, sorry, this is not going to be negative. So this t divided by tau. He says when t becomes tau, what will happen? So very, very simple. This is going to be negative ln V divided by 8. If this is this value itself, this whole fraction becomes 1. As simple as this, x divided by x is 1, right? So if t is equal to tau, tau divided by tau will become 1. Simple mathematics. So we've effectively shown what is required. The next step, he says, determine the time constant from the graph. No problem. So we understand that the value of ln V by 8 will be 1 if t is equal to tau. That was the condition, right? Right? So if I go back to the graph, at this location, I realize that this value should be 1 only when I put such a time that is equal to the time constant. So when you pick this value from the graph, please make sure that you use a dotted line and do this, right? So this will be approximately 3.2 seconds, I guess. So count the number of boxes, mention on the graph, and mention that you've taken the value from the graph at ln V by 8 equals to 1. Time at that point is 3.2. So mention what you've done. Calculate resistance. So tau equals to RC. So tau is 3.2, R we don't know, and capacitance picked from the previous part that you calculated as 5.6 power minus 5. So 5.6 power minus 5. So this will be my R equals to 57 into 10 raised to power 3 ohms, kilo ohms. So this will be 57 into 10 raised to power 3. In the marking scheme, they've written 5.7 power 4, does not matter. Question number 7. This is a Hall probe, and we understand that Hall probes are used to measure voltages. But when we use them to measure voltage, the voltage is representative of the strength of magnetic field. So Hall probe basically tells you the value of magnetic flux density by measuring the tiny voltage that may show up. So there is a current through the slice, there is a thickness of the slice, there is a magnetic field, and there is a semiconductor device. Okay, good enough. Why do we use a semiconducting device? So we have the formula for Hall voltage as VH equals to BI divided by NQT. QT, right? So we have the value of X is mentioned. Semiconductor material charge carriers, which is the value of N, is mentioned. Current is mentioned. The voltage is developed. Okay, fine. So this is the graph for the magnetic field or the magnetic flux density. Show that B, when equal to this, the Hall voltage is this. No problem. So VH equals to IB divided by NQT. So the current at that point, or the maximum current, is 5.4 because it's a constant current. So this will be 5.4. The value of B, maximum shown as 4. He says when it is 4, divided by charge carriers, which is 1.5 power 16. The thickness given in the question is 1.8 minus 3. So 1.8 power minus 3. And the elementary charge is 1.6 minus 19. This Q is a standard value. When you calculate this, this comes out as 5.0 volts. So we have shown what the examiner wanted us to show. The next graph is about Hall voltage. He says, sketch the graph for Hall voltage. No problem. We will see what the equation represents. So VH is equal to BI divided by NQT. Let's see what the dependency is on. So does it depend on the value of B? Yes. Is the value of I changing? No, the current is constant as he mentions. the value of N, charge density, is constant, Q is a constant itself, and T is the thickness, that is also a constant value. This thickness is fixed. So really, Hall voltage is depending on the strength of the magnetic field. So if magnetic flux density changes, Hall voltage changes accordingly. So we move ahead, and basically the shape of the graph will look like this because it's proportional to that, right? But what about the values? Since we are supposed to write down values, we will go down and first see where we find the first constant values. So here we find the first constant, here we find the second constant. What is happening in this region? How much voltage was generated? 5 volts were generated. So somewhere along the center, I will draw a straight line, horizontal line, where we have 5 volts. And before that, we can see as the magnetic flux density was increasing, the Hall voltage will also be increasing. So this will also match the graph because they are both proportional. There is no discrepancy between them. We only have to care about the values. Then up to 0.5, the value comes down again, but I need to make sure where does the value start. So the value comes from 4 to 2. A good idea would be to actually calculate this, or you can say re-evaluate this whole situation or this whole equation, and instead of 4, put 2. But you can see that when you do that, the whole answer gets divided by 2. So instead of 5, I might get 2.5. So standard 2.5 approximately at this point. So from this point onwards, this will be a 2.5 volt. And similarly, matching the graph, it will go something like this, right? So this is the reason why this graph is actually like this. Moving on, part B, he says that there are 3,000 turns. They have replaced the slice with a coil. Cross-sectional area this much. This is A, this is N. He says there is an EMF. He says, show that the EMF is this at 0.010 seconds. So the formula for induced EMF goes something like this: rate of change of magnetic flux. And if there are a number of coils, then this formula becomes N delta phi divided by delta T. And if you go deeper, then phi, or magnetic flux, is equal to magnetic flux density multiplied by cross-sectional area. So this becomes NAB divided by change in time. Now, are the number of turns changing? No. Is the area changing? No. But we do realize that the magnetic flux is changing. So delta B divided by delta T is what is going to control the EMF. So what can I do about B by T? Do I have a graph of B by T? Yes, we have a graph of B with T. So we can calculate the changing value of B with respect to time T. Now, since he said that the time stamp is actually 0.1 second, so this is where that exists, I need to find the gradient. I need to find how much B changes with respect to time. So effectively, he's asking me about the gradient, right? Or gradient for this section will give me the value of B by T. So what I can do is use the last value because the starting coordinates are 0, 0. So it will go something like this as 4 minus 0 divided by 0.02 minus 0. So effectively just 4 by 0.02 with, of course, respective powers. So let's replace these values in the question and see what happens. So N, my EMF was equal to N, which was 3,000 turns, cross-sectional area, which is 3.4 power minus 4, 3.4 into 10 raised to the power minus 4. Delta B by T is actually 4 into 10 raised to the power minus 6, I guess. This is minus 6, yep. Divided by 0.02 with no prefix. So 4 power minus 6 divided by 0.02. This is my delta B by delta T. All right. So this comes out, when you calculate this, this comes out exactly as 2.0 into 10 raised to the power minus 4. So we've shown what the examiner wanted us to show. Now it says sketch the graph for EMF. Very scary graph, but don't worry. So let's write down the equation again to find the dependency. So E is equal to NA delta B divided by delta T. Are we depending on the number of turns? Are they changing? No. Cross-sectional area changing? No. So E is only proportional to the gradient of that first graph that we have over here, right? So let's go through this. So do we have a gradient over here? Does B exist? Is B changing at all times? Is the gradient existing? Yes, the gradient is changing. So in the first section, we have a voltage of 2 volts, right? We'll get to the signs later, but first let's draw the graph. Let's observe this next section. Is the magnetic field changing? Is there any slope? Is the value of B changing? It's not. Is the value of B changing in this section? It's not. So as long as the value of magnetic flux density is not changing, I will get a 0 voltage, right? up to 0.5. Okay, no, I think let's go back to the graph. Yeah, so from 0 to 0.4, I get a 0 value because the magnetic field is not changing. From this region, 0.4 to 0.5, I can see that the magnetic flux is changing again. Be that positive, be that negative, we will discuss that later. So this becomes an EMF over here up to this point. But then again, we get 0. Because in the last section, there is no change in magnetic field. If there is no change in magnetic field, the EMF becomes 0. There needs to be a gradient. Now let's move on to the sign of these EMF graphs. You see, including the Lenz's law, the equation actually becomes a negative delta phi divided by delta t. So if the gradient of this of this magnetic flux density is positive, EMF will be negative because of this negative sign. So there is an opposition. So right now we have a positive gradient of magnetic flux, and over here we have a negative gradient of magnetic flux. So the signs will be changed. So if this is magnetic flux was positive, then the EMF will be negative. So in this region, I get magnetic flux to be positive, but EMF will be negative because of this equation and Lenz's law. Similarly, when I move to the next section, I see that the gradient is negative, so the EMF will be positive. So that is correct. So in this section, I have a negative magnetic field or magnetic flux density, but positive value of EMF, right? So that is why this is positive. This is the true graph of this system. Okay, all right. Moving on, state the meaning of photon. So photon is a packet of energy that belongs to an electromagnetic spectrum. So it's a packet of energy belonging to the electromagnetic radiation spectrum. So just memorize these definitions from the marking scheme. That's simple as this. When the surface of metal is illuminated, electromagnetic radiation, electrons start. So this is the name of the phenomena is photoelectric emission. It says it is observed that the frequency of the electromagnetic radiation is greater than a certain value, only then, regardless of the intensity. Explain how this observation provides for existence of photons. Again, this is a repeated question. Memorize the marking scheme answer. I understand that this is a very vague question. We already understand these things, but what are we supposed to write down? So, in these questions, simply state down the facts. Just write down the facts that you already know. So, you will write down that one electron only causes an ejection of one photon. This is a fact, right? You will write down that the energy, it's the other way around. One photon will cause one electron. So, one photon will cause only one electron. The energy of the photon is equal to the energy of the electron, right? And it is, or electron only emitted when it has energy more than a certain amount, which is calculated by HF, as this is the work function. Okay, so then you will write down that energy is absorbed as discrete packets, not as a range of energies, just like we do in microwave. If you heat up a food in microwave, it gradually heats up. That is an evidence for light or electromagnetic being a wave rather than being a packet. Next part is part C, shows the variation of maximum kinetic energy. Okay, fine. And if you extend this below, you will realize that this graph actually starts from another location. Okay, all right. Let's move ahead. So he says, what does the gradient of the line represent? So how can we do that? So we have energy divided by frequency. So we have E equals to HF. So if I take F over there, this becomes E divided by F equals to H. So this is Planck's constant. So the gradient is representative of Planck's constant. Why did we do that? Because we have y-axis as this and x-axis as this. So the gradient is actually change in y divided by change in x, right? Okay. So moving on to the next part, the previous part, the y-intercept of the extra plotted. So if we were to carry this over, what would this represent? Since the kinetic energy will become 0, right, at that point, or the frequency becomes 0 at that point, because we increase the frequency at this point. So this will be the minimum amount of energy required for the electron to eject. So this will become the energy of the work function. So this is the work function energy with a negative sign, because in the graph it has to be extra-plotted. So it becomes a negative intercept. The fluorine is a radioactive nuclide that is used in tracers. Okay, fine. As I mentioned in my classes, you have to memorize this equation. Now it's right in front of you. He's asking the same question again. State what is meant by a tracer. So tracer is an element that can react or that can be absorbed by your body, so that can release radiation. So it can help trace where the cancer cell may be. So it is a substance inserted in the body or injected in the body, so it can be absorbed easily. That is its specialty, absorbed easily, and then helps detection outside the body by releasing radiation or by releasing any sort of electromagnetic spectrum wave that can be detected. State the symbol of the particles. So this is just an equation. So we understand that due to the fluorine decay, we have, this is an oxygen element. So this will be 18, because we know that X should be a positron, right? So P is 1, R is 18, Q is 0, and X itself is a positron. So this will be B plus. Now we could have written down positron, but since he says state the symbol, that's why I'm writing down it as a symbol. Explain how the reactive decay of fluorine results in the emission from the body of the gamma ray. So this is again a PET scan process that you generally memorize. Okay, so positrons are emitted. Positrons are emitted by the decay process. Okay, they annihilate. This is the key word. They annihilate the electrons of the active site, or the electrons already present inside the body, right? And their mass becomes energy, which is released as gamma radiation that can be detected. Explain how the detection of gamma ray photons is used to produce an image. No problem. So the affected area has higher activity, leading to higher radiation. That's why it will light up in the detector as being very radioactive, right? And the arrival times means how quickly or how late they come to the detector, can help pinpoint the location inside the body. The half-life fluorine is T. N is the substance, which will be moles primarily. Yes, this is moles. Determine expression for R naught, the rate of production of gamma rays. Now, for the rate of production, we have a formula that is A equals to lambda N. N is the number of atoms and A is activity. Activity is primarily decay per second, right? So he is asking us about R in this format or in this equation. So let's write this down. So what will be N? So N, the number of atoms, will be equal to moles multiplied by the Avogadro's number, which is Na. So we can replace this over here, but let's find for lambda. So we have an equation that lambda is equal to ln of 2 divided by the half-life. As he mentioned, a variable for half-life. Yes, that is T. So this is going to become ln of 2 divided by T. So we have the variable for lambda, we have the variable of N, we have their equivalent representatives. Let's combine them together. So A equals to lambda N. A gets replaced as R naught, right? Equals to lambda gets replaced as ln of 2 divided by T. N gets replaced as moles, N multiplied by Avogadro's number. Now, since he's asking us about the gamma ray production, we understand that due to the annihilation of electrons, there are 2 gamma ray photons always produced. So because of this annihilation, 2 photons are produced. So this will be a 2 added in this. So this becomes 2 ln of 2 n a divided by t. Then we have this equation r naught with t. So let's take everything out from this equation. So we have r naught equals to 2 ln 2 n a divided by t. So I can see that r naught is inversely proportional to t. Very simple. So at the very beginning, we would have maximum concentration, and with the passage of time, they're going to get halved because this is a half-life. So this will be r naught by 2, and this will be r naught by 4. So first coordinate at this point, and this will be 2t. This will be half of half. This will be the new coordinate. So then you simply draw a line through them, which is actually the line for the half-life. It's a sketch. You have to be rough, but of course there is a reason behind it. Question number 10, Wien's displacement law. So when you write down Wien's displacement law, just simply mention their representatives. So we have, we will say that the maximum intensity lambda is inversely proportional to temperature. So simply write down that lambda max is, or lambda is the wavelength at maximum radiation or maximum intensity radiation, and temperature or temp is the surface temperature. We have to clarify where the temperature is. Are you talking about the core? Are you talking about the surface? What temperature? So this is how you explain this, right? Cosmology student, okay, there is a story here, you can read this. The student observed the radiation from the star is redshifted as mentioned by Doppler effect. He says, state what is meant by standard candle. So it's an object or a star of known luminosity, the one that we used to compare for others. For example, our own sun is a standard luminosity, is a standard candle. State the reason why the radiation from the star is redshifted. It is because the star is moving away from us. It's moving away, right? And moving away from the observer. And this is because of the Doppler effect. Let's move on to the next part. He says that he's using so and so values to calculate these things. So let's move on. This is where the story is written. He says he's using Wien displacement law to estimate surface temperature. He's using standard candle to estimate the distance of galaxy. He's used Stefan-Boltzmann law to estimate the radius. Let's write them down. So we have Wien's law as lambda t or lambda max equals to a constant k. Then we have the standard candle model. So for a standard candle, we had the formula of F equals to, L equals to, luminosity equals to radiant flux density divided by 4 pi d square. This was the distance of the galaxy. Equals to the Stefan-Boltzmann law or SB law, which was equal to F equals to 4 pi sigma r square t4. So this is what he's using for everything. So let's read the first one. He says wavelength. Now, whatever the student has done, student has not corrected for the redshift. He is not considering them. So what will happen to the wavelength of the radiation that he measures? You see, due to the redshift, the wavelength gets reported to be a bit higher, right? So if the wavelength is higher, then we will consider this to be, this example, too high. Wavelength is too high because of the Doppler effect. Then surface temperature. Now, according to Wien's law, now of course we understand there's a mistake of the student, but what has he done? He has mentioned or he's measured the value of lambda to be too high or too great. So if lambda is greater, what happens to t? So let's t equals to k divided by lambda. If lambda is high, t is low. So the surface temperature measured will be too low. Moving on to the distance of the star, which is calculated by this formula. Do we have any influence of lambda in this equation or the changes in lambda in this equation? No, we don't. So the student's values of distance will be the same. There will be no change. There will be no effect over here. So the last part is radius of the star, right? So for the radius, we have to use this formula. Okay, so we go to this one. But this will be in steps or parts. You see, what happened with the first law, the Wien's displacement law? Your lambda was greater than the expected value. The temperature was lower. So if the temperature was lower, right, if you had to keep F constant, because this F does not change, then the value of R has to increase. The value of R has to increase because everything else is a constant, right? So, or you can make this equation as T4 equals to F divided by 4 pi sigma R square. Since T is reported to be too low, R will be reported to be too high. So this will be too high, right? Okay.